Okay, so hello everyone. I'm Hamish Knox. This is Microservices, Scalability and Resilience, or How I Learned to Stop Worrying and Love Distributed Systems. So, I'm going to do something that most people don't start off with, which is a disclaimer at the start. First of all, nothing I say is representative of the views of any past, present, or future employer or educational institution. Of course, I have several of those. I'm not endorsing any product or service within this lecture. I'm going to talk a lot about one particular service, but that's just because I worked there and used a lot of it. There are no internal secrets in this lecture, everything is publicly available, and some people will tell you that all of this is overkill technologically. As with all engineering problems, there are massive trade-offs to be had. This is why we get paid the big bucks, because we make these decisions. And this is not a PhD level thesis on networking, distributed systems, or other academic fields. It's about the practical nature of software engineering in the modern world. So why am I qualified to give this masterclass? Well, as you know, fifth year MEng, former team principal at HW Racing, where we built racing cars. That's me with my management team there. We had 100 team members, 30 grand budget. So although it's not directly software engineering, it was a large integration problem with multiple different teams working on the same thing. And this is something we're going to see pop up later. And I spent 6 months working for Amazon on the Prime Video web organization. Hello.
Oh, sorry, we're late.
No worries. So this is me in the Amazon Video Operations Center. We're monitoring live feeds and so on. This is the nice big building in London where I went to work every day. So there's some prerequisite knowledge for this. You need to be able to read and write production code in at least one back-end language. You need to understand the basics of how the web works, fundamental software engineering, how to work with databases, general system design concepts. But everyone in this room should have this. I build on stuff that's taught throughout previous courses. This will not be out of the realms of possibility for anybody else. And there's a few learning outcomes as well. So you're going to learn how modern web systems work, why organizations move to microservices, and why you probably shouldn't, how to design horizontally scalable systems, which I absolutely love, and the trade-offs involved in such systems. You're going to learn how to recognize common pitfalls and anti-patterns, what looks obvious but you should never do, and you're going to appreciate the application of core data patterns at a conceptual level. Here's our agenda, various different parts, we don't need to go into detail on that. And what we're going to do throughout this whole lecture is we're going to look at a problem, try a naive solution, right? We're going to try the first thing that comes to our mind. Naive doesn't mean bad, it just means that's the first thing that comes to your mind. We're going to find where that breaks and then try a new solution. So, part 0, modern software. Most people don't download and run programs anymore. This isn't the 1990s, and even if they do, there's likely a backend somewhere online. This is Facebook, a sort of archetypal example of something you have in your browser. You don't download it at all in the classical sense. Discord, right? That's something I know most of you have. It's an application on your computer, but it still talks a lot to the back end, and even something like CAD, former student people will recognize this particular image. There's a lot of complex mathematical calculations on your computer, but it still talks to a back-end service for most stuff. So that's when we end up with the client-server model, right? Nothing pushing the boat out. You've got your client here sitting on your computer. You've got a server with logic and a database. That's how things have worked for years. So what happens when your system becomes popular in that client-server model? You get more users, more requests, more data, more concurrent activity. You get traffic spikes. And if you're using an old Windows box, you end up with this sort of thing. So let's, again, try a naive solution. Add more CPUs, add more memory, add more network bandwidth. Does anyone recognize this? This is a screen from AWS EC2. These are different instances you can rent over time. Shows different CPUs, memory, etc. But you can see it only goes up to a certain size. Why does this break down? Does anyone have any ideas why this breaks down? Feel free to shout out. No worries. We hit physical ceilings, right? We hit physical issues with the silicon. You get diminishing returns, right? The 50th dollar you spend is less efficient than the first dollar you spend. And you end up with a single point of failure. It's not elastic, right? If you have lower demand, you can't scale down. If you have higher demand, you can't scale up. You're always paying for this. But some companies still do this. Sometimes you need to have everything on one machine. Banks and airlines love these great big IBM Z mainframes. I actually know that Lloyd's Banking Group has an IBM Z in Edinburgh, at least one of them. So let's try a solution. Let's move from one big machine to lots of more modest machines. I say more modest, not cheap, because they're still like the price of a car, but still, we scale out rather than up. It's got a handful of advantages. You can scale unlimited. The infrastructure is much cheaper, it's fault tolerant. But how do we get our requests to all these different machines, right? You have a bunch of servers running your code. How do you get them there? How do you pick an individual server to serve requests? We have all of our users here, all of our servers here, what goes in the middle? Anyone have any idea how we can route requests to a machine? Varun?
Load balancer?
A load balancer. How might we load balance?
Well, depending on which machine is quieter, you could send them traffic.
So you've skipped the naive solution altogether and gone to something much better. So our naive solution tells us how do we get to servers? We use DNS. So well done, Varun. DNS, right? This is how things used to work. You would have your DNS server up here. Every time you make a DNS request, it gives you the response of one of these different servers. It's actually pretty lightweight. You know, it works pretty well in a lot of circumstances, but there are some problems. So DNS wasn't designed for this. There's no health checks, so if a server goes bad, it still sends it to you, as demonstrated there. And DNS is cached a lot. It's cached at every single level, which makes it really efficient got really bad for this. It doesn't consider existing load. So we end up with a reverse proxy load balancer. We send them all a request, this central thing in the middle, and then it goes to a bunch of servers. So we can use commodity hardware with something like Nginx. We can use proprietary appliances. Amazon used to use these things called net scalers, which cost basically as much as a car. It distributes requests, it performs health checks, it removes failed nodes, it does all that great stuff. And you can assign to it a number of algorithms. So round robin is the classic one, where you just go back and forth between all them. Least connections, right? Keep track of what connections are active and route to the one with the fewest open connections. That makes a lot of sense. That's what Rune was getting at over there. Weighted balancing, you assign a different weight to each server. So perhaps some are further away, some are less powerful hardware. This isn't used that much in practice, but it's still good to know. And source IP hashing. So if you use consistent hashing, if anyone's done big data, you know that you send in a hash, it spreads out over a ring, and it truly just randomly distributes requests, which sometimes is what you want, most of the time isn't. But there's a problem. Can anyone spot the problem? Hamish?
1 point of failure?
Exactly, 1 point of failure. So what you look to instead is highly available load balancing. So you have multiple load balancers sitting together, right? They share state like this. There's lots of different techniques to do it. Shared memory, lots of proprietary stuff in there. You know, Netscaler will sell you 2 of them that sit together and talk to each other. It's massively expensive, like really expensive. Amazon no longer does this because of how expensive it is. And it's still fairly centralized, you know. If these 2 things are sitting in a rack and they both go out, then you're still screwed. And it's hard to do effectively. It's a really difficult distributed systems problem. So what we do instead, we move to the cloud, right? Use AWS Elastic Load Balancer. We use Google's Cloud Loads Balancing. We use Azure's Load Balancer. They handle the tricky stuff for you. There's lots of proprietary secret sauce in there. It's fully distributed across a large number of nodes, and it works if your stuff is in the cloud, which is nice because you don't have to deal with hardware. So, anyone remember F20DC, data communications and networking, where we dealt with this OSI model? So we think, what layer does this distribute things at? Well, physical doesn't make sense, right? We're not sending pulses along wires to different things. Data link doesn't make sense. We can keep going until we get to level 4, right, where we're dealing with TCP. So you stick a load balancer in, you route based on IP and port very fast, right? Oh, we've gone to the problem section too fast. So your connection goes in, routes up through there, and routes up to there, and you establish a TCP connection from the user to the server. Can anyone think of any problems with this? No, fantastic. It's a really esoteric thing to get your head around, but there's lots of redundant reconnections, right? Every time you route your connection through here like this, you're establishing a connection between here and here, and you're re-establishing from here to here and here to here and here to here, whereas actually those connections are remaining constant. And also you need to give an SSL certificate to every server. That's a real pain if you're managing security. So to instead move a higher level, move to HTTP, where we reuse the connections and we terminate SSL at the load balancer. That has the notable disadvantage of allowing the NSA to listen to this sort of stuff, which is genuinely what they do. They released a paper about doing it at Google, but it's probably not an issue unless you're working for the Russians or something. And it also gives you an extra level. So this is the only thing that gets exposed to the internet. Your servers never see anything. You can use non-standard ports. It's great. So you have your connection here and your connection here. Now, statelessness. This is the single most important thing about horizontal scalability. If you're routing to a random server each time, you cannot guarantee to have the same server. Your state cannot be stored on the server whatsoever. You can't have any cache on there. You can't have any in-memory database. It does not work. Things break down in a horrific way to debug. So think of functional programming, right? We have our input, we have our output, we transform that, we do nothing in between, we store no state. It's get that hammered into your head. We store no state in services. So how do we manage data, right? Here's a naive solution. Add an external state store. Stick everything to a database. Can anyone see any problems? Hamish?
Single point of failure.
Exactly, you're on fire. But actually, is that a problem? How complex is your logic? How much state are you storing? How often are you storing it? Have you taken any measurements? Measurements is such an important thing because we can end up building massive systems when we don't actually really need them. If you're not taking your statistics, in particular percentiles, what are 95% of your users experiencing? What are 99% of your users experiencing? You are gambling based on smoke, right? Do you even need to scale? Can one solid box run it? So let's say it is a problem. How do we solve it as academics? We build a distributed state layer, we do sharding and partitioning, membership and failure detection, forms and durability, consistency trade-offs, start looking at papers that look like this? No, don't do this. Use somebody else's product. Your customers pay you to solve the problems that you have said you will do. They do not pay you to write databases. It's so important. This is all, we are practical engineers, we're not academics. We are solving problems for customers. Amazon has 14 leadership principles. Number 1 is customer obsession. Everything flows from that. Use DynamoDB. Always use DynamoDB. It's great, right? It's fantastic. It requires a bit of a workaround. This is not the 400 level talk on that. Use it. Come and talk to me afterwards if you're interested. I'll show you a good talk. That's Aurora. That's a fully distributed SQL database, something which we thought was impossible. It works really well, and it's also scalable. So rather than having an instance running 24/7, it scales down and scales up as you need it. This is RDS, right? A standard database service. You're just running a database server. Amazon handles updates and patching and so on. Not an endorsement of Amazon. These are just the products I'm familiar with. Use Google, use Azure, use Alibaba Cloud. I don't care. And finally, Redis, right? Or Amazon MemoryDB. This is a fast in-memory state store. It works really well for caching. So how do we manage data at scale? Well, we keep one database per service, right? Every server, or every group of servers doing a service owns its own data. We don't communicate through the database, we communicate through API calls. You don't couple things together. You have autonomy, you have explicit API contracts. All of this will go into depth later on in the talk. Don't get scared by this talk. And you probably don't need strong consistency. So any of you who have taken big data will understand the CAP theorem, understand that when you move to scale, if you want consistency, availability, and partition tolerance, you can only pick two of them. However, strong consistency is not that important. When you write to a database, it's probably not that important to get the result back immediately, as long as it's eventually consistent. I know it sounds mad, but you're probably not a bank writing banking code. If you are, fantastic, use a SQL database. But we will go later on into design patterns that avoid strong consistency, particularly in the lab. CQRS, right? Does everyone know about this? No, so it's command query response, command and query request separation. So your API calls that are commands that are telling the system to do something should be separate from your queries, the ones that are getting data. As soon as you start mixing them, all sorts of bad and difficult to debug things happen. Commands and queries kept separate. And keep your analytics data separate from your working data. If you're an engineer, if you're in a business, you want analytics data. You want to understand how your customers are acting, how to improve your system. OLTP is online transaction processing. That's your working data. That's your transactions in and out. That's your API requests. Online analytics processing, that is your analytics data. That is your big data, your stuff you train your machine learning models on. That's what you keep in AWS Redshift or Oracle DB or whatever. And they have fundamental different models. Your data science people want different things than your programmers do. So we move on to part 3, microservices, and this is where it gets fun. I'm also aware I've been talking exceedingly fast, so please tell me to slow down if that's an issue. It's just how I talk, as people at the back will already know. So what is a monolith, right? Anyone seen 2001: A Space Odyssey? No? Awesome. This is the monolith. It spurs human evolution from chimps and they start attacking each other and so on. But actually it's this, right? It's that same thing we saw at the start. You have this one box where all your logic is. It might not have your UI, that might be up here, but it's where all your logic is. Now, there are lots of advantages to it, right? It's simple to develop. You have a simple Git repository with your software in it. It's easy to run and test. You have a single block of code you can turn on, you can put inputs in, you can see its outputs, and it's really straightforward to debug. You can jump in with breakpoints or print statements or logs or whatever, and it's strongly consistent. What I said before about not needing strong consistency, it's still really nice to have. You know, once you do this, this will happen. Input, meet output. And it's also really easy to run. You have a single executable, you have a single repository that things are working on, that's great. But there are some technical difficulties associated with the monolith. Tightly coupling, right? You have this bit of software, you have this bit of software, they're intermingled with each other. It's very hard to separate two functions in the same file all the time, or a method from a class. You've got slow builds and deployments. Imagine if Amazon had one single executable that ran all of their code. It would take years to compile, years to deploy as they run all their tests. And there are scaling limitations. As said before, you can only scale so far with one piece of software. And technology lock-in, right? If one part of your team wants to use this bit of technology, another part of your team wants to use this bit of your technology, then that's very difficult to do. It can be fragile, right? If something breaks, it freezes everything. And another thing that I've not mentioned there, I'm sure I'll come back to me. Now, but the most important problems with a monolithic piece of software are organizational, right? You've got source control and merge conflicts. You've got somebody working on the front end and somebody working on the back end, and they're conflicting with each other, and you end up getting commits that you don't really want. Your ownership becomes unclear. It's really important for everybody to know who owns this bit of software, who's responsible for this piece of code, because you want to know who can fix it. Ownership is something dramatically underrated in the software development process. And it's hard to expand the team beyond a certain size. You know, too many cooks spoil the broth. Too many people working in a small shared space of software becomes really difficult. So how do we deal with that? We break up the monolith. We start with an unstructured monolith, that's all the stuff we've just discussed, and then we can move to a structured monolith. So you might have a class that's a controller for a database. You might have one that handles domain data, right? One that handles your transactions. You might have different files for the functions. This is probably where you want to be 99% of the time, right? Your structured monolith. Structure your code well, have controllers, domains, separate out things by file, even if it's a one-man development team, this has tremendous use, right? Split things out into libraries. And then free modular monolith, where you have clear modules and domains. You're not all writing in the same Git repository. You can have separate packages, namespaces, modules, several bits of software talking to each other. But what if we could go further, right? This is all still one piece of software running on one computer. What if we split the monolith into separate services? This will not be alien to any of you, but how it's done might be. Services can be clients of other services, and each one is an independent unit that can call other services. This ends up in what we call a service-oriented architecture, where your entire computer architecture is based on this service here providing this data to this service here. So you end up with something like this here, where you have your client at the start making requests to services rather than that one at the start for different parts. This part might control part of the UI, this part might control part of the back-end logic, and then it makes requests to further services. Now I've added this shape in particular, this diamond that comes back, because this is a really common thing that you see in microservice architectures, where you have some state authority here that has a database behind it, and then you've got two different services taking out different bits of the data or different uses of the data, and then they get combined back together to form the final request. So this particular one is fine. What you don't want is a circular dependency where things revolve round and round because you end up in dependency hell. So how do they actually communicate? It's normally HTTP, right? Again, those of you who remember data communications and networking, that won't be a major surprise. HTTP is a great protocol for talking between computers, but it's not the end all and be all, right? It's at layer 7, but there's stuff above layer 7 that we need. So people often use REST APIs, there's GraphQL, RPC frameworks. So what is REST, right? The idea is that it's representational state transfer. You have state on one machine, you want to take it to the other machine, that's where you get it across. Everything's treated as a resource. So yeah, each endpoint is a resource. You can do these different things on resources. So this might be, let's say it's Amazon, I'm a customer of Amazon. This might be a resource. You might be able to get the user that is me, I am a resource. You might be able to post an order to me, right? That order is now a resource. It's all about these data controls on these resources. But in reality, that's not how any of us use REST. It's not how I use REST. Most of the time, it just means calling a function over HTTP with JSON, right? Post/API/ you put a request in the body. If you're interested in this, look at Richardson maturity. It's not actually that important directly for this. But yeah, that's how most people use REST, is they just set up API endpoints, send data forward and send data back without caring about the underlying nature of how things are represented as resources. And GraphQL is becoming increasingly popular, where you shape your request in the way that you want the data. So here's an example. You might ask for a human whose ID is 1000 and ask for their name and their height. We end up with Luke Skywalker, whose height is 1.72, presumably meters. So the request shape is the same as the response shape. However you change the request, the response will change in turn. It's a really cool thing to do if you care about accessing resources, but actually, we don't always care about accessing resources. Sometimes we do just want that model of, here's some code on another machine, we want to run it. This is what we call remote procedure calls. So there's various frameworks for this. We've got gRPC by Google, we've got ConnectRPC by an open source group, we've got Twerp by Twitch, now owned by Amazon. But that leads to the really important question of how do we handle interfaces and boundaries between systems? Well, most system design can actually boil down to the boundaries between systems. It's all about having your edges, these black box edges defined, and then filling in that black box. If you start out your system by saying, this talks to this and this talks to this, and here's what this requests data-wise, then you can build a whole system. You care about what a service does, not how it does it. This is declarative code rather than imperative code. And most microservice software engineering is exposing functions to other services. It's saying, I have this data, you can have it within this certain amount of time, or I would like this data from you. So we end up with these interface definition languages to define that. So protobufs, that's developed by Google, that's binary serialization over HTTP. Smithy, that's done by Amazon, is used a lot by Disney now. And it lets you do design by contract. So does anyone here take rigorous systems in 4th year or 5th year? No, okay, fantastic, that means I can talk about this. So it lets you design by contract. You define your system by saying, this is my contract, right? This is the request that I take, and this is the response that I give. You can see it takes a query, a page number, and results per page, and it gives back this response. And you set up a service saying, this request returns this response. You open up your code. All you have to do is take this as your input, take this as your output, and write a function. Now, I appreciate saying all you have to do is write a function. It's really complicated, right? All we do is write code. That's a tremendously complicated thing. We go to university for 4+ years to learn how to do it. But knowing what you're being given and what you can give back is really important. This is the big thing I'd like to take away from this section here. You should define your boundaries like this. You do this before you even write your code. It's like test-driven development, except people actually do it. So you have your inputs, you have your outputs, and then you define what happens based on that. So what you can do with that then is you can build a software development kit, which is effectively language bindings for that. So if we go back, what this might mean is, although this is in no particular programming language, it's actually in protobufs, what you do then is SDK transforms this into, say, a Java class if you have a Java SDK, or a Python class if you have a Python SDK. And this then gets turned into a function. So what you do is you pass in, you create this class in Java, say, then you pass that class into this function, and then it returns one of these classes. And you do all of that without leaving Java. It's all language native objects. It's fully typed as well. So we all know how useful type systems are. If you don't, then head along to Mercaz's lecture tomorrow morning. And it takes care of retries, backoffs, etc., which we'll get into. Basically, retrying when things fail. And the SDK is tremendous because as well as your code being auto-generated from your interface file, the SDK is automatically generated. I'm doing this with a startup I'm trying to found right now. If anyone is investing, then please let me know. So this leads us to idempotency, an extremely useful thing, not impotency, that's very different. You want each operation to happen only once, right? You get sent a request. So let's say you're doing a transaction from one bank account to another. You want your request to happen only once, but the real world is messy. You cannot guarantee that this will get across. It's the two generals problem, if anyone's seen that Tom Scott video. You will send a request, you can't always guarantee you get a response back, so you send it again. So how do we deal with this? How do we deal with this? How do we solve the problem of not knowing whether things are happening at least once, more than once? Anyone have any suggestions? Well, we do what's called an idempotency key. That's a unique key associated with each request. It's a short random string normally. It's often a UUID, which is 128 bits. Anyone know how big 2 to the 128 is? It's massive, right? If you made 1 billion of these every second, it would take 10 to the 22 years to exhaust them. The universe is around 10 to the 10 years old, so there's literally trillions of times the age of the universe. And this is really important because if we go back to our horizontal scalability thing, we can't guarantee that we're generating a different ID from everyone else. If all of our nodes on the network are generating different UUIDs, this functionally guarantees they can't collide because there's so many and it's randomly generated. So that's all been very theoretical. Let's put it into practice. Let's have a food delivery app, right? That's Deliveroo. You have your front end that sits on your phone. You've got all these different services. Order service that might handle payment processing with the help of the payment service. It'll handle menu selection. It'll handle discounts. And then once that's done, it will send a message over this pipe here, where the interface has been defined by an IDL file, so like protobufs, to the kitchen service. And that will call the delivery service once that's ready. All of these things will call the notification service, which will send a notification to your phone. The beautiful thing here is each of these can be taken care of by a different team. And so long as each team knows what's on these boundaries, they can work independently. If the kitchen service knows, okay, we have these inputs, we have these, this accepts these inputs, this accepts these inputs, their solution space is dramatically constrained. And not only does it allow them to do the work easier, it allows them to do extra stuff with their work. It allows them to reduce their latency. Once you have that problem locked down, this diagram is the hard bit. Defining the boundaries between the systems is the hard bit when it comes to sort of system software engineering at this scale. So, how do we actually deploy these things? What next? We have a system made up of all these microservices that are massively horizontally scalable. How do we actually run it? Anyone have any ideas on how we put this code onto machines and run it? Yep.
Containerization like Docker and Kubernetes and stuff?
That is an awesome thing to do. But you're 2 steps ahead of me.
Sorry.
Your naive solution, you're too smart for this lecture, is you build a big data center full of servers, right? That is an actual AWS data center. It looks like something aliens have built because it basically is. You put the code in each server via FTP, you maybe even write a script for it, right? And then you run the code. But can anyone see any problem with such an approach? Not you. Scalability, that's a big thing, right? If you're having to do this thousands of times, as you might do if you're in a massive data center, like they're trying to build out Edinburgh West, that becomes a problem. It's really difficult. You end up with lots of capacity that isn't used. If you just have one piece of code running on each server, then your servers are likely to be much more powerful than your code can take advantage of, right? As we know from our operating systems and concurrency course, it's really hard to make code that runs on all cores of a CPU equally, that utilizes all of those resources. So do we deploy multiple services on each machine? Well, we end up with overlapping ports, right? You'll probably want to take HTTP requests. It means you probably want to take it on port 80. That means if you have multiple things going on port 80, you have to split things out into different ports. That's very difficult. There's no isolation, right? If one of your machines locks up the operating system, then it affects all the services. And you've got conflicting dependency versions. If I have one service that uses the C standard library version N, and another one that uses the C standard library version N++, then normally it should be fine under most language systems nowadays, but it can still cause issues. So VMs is our first solution, right? Abstract your hardware away. Each team who makes one of those microservices says, okay, I need this many vCPUs, I need this much RAM. And then you assign multiple VMs per machine. You use orchestration tools like those developed by VMware, now owned by Broadcom, so nobody uses them anymore. You end up packing much more efficiently. You end up with multiple services per machine. It's awesome. The VM hypervisor handles all that port forwarding stuff. But there are some problems, right? Do you really need a whole machine, a whole virtual machine for your code? You have to deal with OS updates, you have to deal with scaling up or down, right? If you're starting a whole virtual machine, you know how long it takes to start up a Windows machine, not that you're using Windows for this. And it's still relatively inefficient, right? Again, what do your customers care about? They don't care that you're running a whole Linux kernel on top of another Linux kernel, they care that you're solving their problem. So what you do, as Hamish at the back so correctly suggested, you move to containers. So containers are great, you probably know this already, but you get isolation without having to care about an OS. It's really easy to scan for vulnerabilities, so lots of modern static analysis tools look at the layers that get baked into a container and say, oh, this has this problem, this has this problem. It lets you get an overall view of your whole software stack and a whole software bill of materials saying, this vulnerable library is used in exactly these different services. Take the log4j exploit that happened. It was a nightmare inside Amazon. I say this as if I was there, I wasn't. But it was made a lot easier by the fact that we were able to look at each container and say, oh, this container uses log4j, let's patch it. We have a detailed record of what goes in each container. And they're quick to spin up and down, right? It doesn't use a whole VM, it uses kernel namespaces. It's awesome. And they can be orchestrated with tools like Kubernetes, as said at the back. So they can automatically restart, they can scale in response to load across multiple machines, it's great. But what if we want to run in the cloud, right? You're a software engineer, again, what do your customers care about? They don't care that you know how to replace network cards and storage and RAM and so on. You have to pay for physical security and hardware updates and data center space and HVAC and backups and networking. Electricity is a massive thing. On-premises systems, some people still do it, right? Back when I worked at VTech over summer, we had on-premises stuff, but it's really complicated and really difficult, and you need to hire people full-time to deal with it. So, and somebody else is probably better at it than you are. So what you do, you move to AWS, you move to Azure, you move to Google Cloud, other clouds are available. Not really. So you've got several options when you're dealing with cloud compute. Again, this is all AWS flavored because that's what I'm familiar with. There are alternatives. Please speak to me about it afterwards. EC2 lets you spin up VMs. ECS lets you spin up containers directly. And Fargate goes even one better because with ECS, you still have to have the VMs underneath the containers to handle all of it. What you do with Fargate is you just say, oh, I want this many containers, or I want each container to only use however much CPU. When it gets above this, launch a new container. So you provide an image, you set scaling conditions, you hit go, and bam, it sends up a million containers and drains your bank account. EKS provides managed Kubernetes, other cloud providers are available. But can we go further? Right, we've abstracted containers. Does anyone know how we can go further in abstraction? No, awesome, that's good for me. So writing software, what is software fundamentally about, right? It's about taking an input, processing it, and performing some action. As we've seen before, we want to keep things pure functional, not necessarily at the individual software component level, but at the system level. What we care about is outputs, not state. I'm sounding dangerously close to someone who uses Haskell here, but I'm not one of them. If you just want to run some code, then a container is a lot to set up, right? And the same with the VM is a lot to set up. We've moved past VMs to containers. What if we can move past containers? You don't always want to have a container running continuously, right? If you are responding in requests to load, a container still takes time to start up, particularly if you're using like Java and you start the Java virtual machine. You can have a minute, or well, probably less, but still upwards of 10 seconds to start a container, which is really awkward if you want to respond to user requests instantly. So what you do, you move to functions as a service. I've used the other cloud providers here as well to be slightly less AWS obsessed, but you've got Lambda, Azure functions, and Google Cloud Run functions. They're event driven, which means that you set up an event that can be an API request, like we saw earlier, get/HamishKnox/orders. It can be a file upload. It can be absolutely anything, and then it's a function that triggers without you having to care about a service. You do not need to care about any of these different things, right? Security, deployment, fleet health, infrastructure. You don't even know what operating system you're running on. You just get a space to run some code, take an input, give an output. It's generally the cheapest if you're running something infrequently. So if you're running an API that only gets called less than once a minute, this is probably a good thing, right? You only care about responding to requests. You don't care about having code running 24/7. And it's the backbone of a lot of Amazon's infrastructure. I cannot speak to any other company because I've not been employed by any other big cloud company, but basically Lambda is the default recommendation for making a new service at Amazon. Your downside being cold start time. So as well as containers having a cold start time, Lambdas or functions have a cold start time. This is less than a container, but it's still non-negligible. So if you have something that needs to respond within millisecond precision, then you want a container. But I'm getting ahead of myself. Which cloud service do you use? Use Lambda as your go-to, as I've said. This is what you should start thinking about if you're wanting to deploy in the cloud. If you need streaming, high-frequency polling, or caching, then Fargate. Caching because it handles consistent state, high-frequency polling because you only deal with the cold start once, and streaming again because it's persistent. If you have hardware requirement access, you need to care about the OS, you need deep security concerns, then run EC2. Try and stay away from EC2, you will need to pay an ops team to run that. And this is a controversial one here, but you probably don't need to care about Kubernetes. Kubernetes has the advantages of handling a lot of stuff for you, but it has the disadvantage if you need to configure how it handles all that stuff. The likes of ECS Fargate, all the alternatives on other cloud providers, they're available. That handles even more of it for you. It's much simpler to use. And going more abstract as we move down up the tree here means you're spending less on operations stuff. It means you don't need people to care about database patches and so on. So, how do we set up this infrastructure? How do you've started a new software company, how do we spin up all these Lambdas, set up all this code, spin up all these EC2 instances? Anyone have any ideas? Anyone set up anything on cloud before? So the standard one is you go to the AWS console or you run the AWS command line interface and you say, oh, I would like to spin up an EC2 instance, I would like to spin up an ECS instance, I would like a cluster, right? You have documented procedures on how to do this, you script some of it, right? That's what we do, we're software engineers. Can anyone see any problems with this way of doing things? It could be slow, yeah, that's certainly one of them. One I don't think I put up here, but that's one that I definitely missed out. If you're having to deal with a human to deal with all this, even a script, then it's an issue, yeah?
It can be like quite difficult to set up all the constant commands and stuff, because I tried doing this before and it just didn't work. So,
Yeah. I've done this before, right? In the third year group project, nobody's here who was with me on that. It was a real pain in the backside. I ended up paying quite a lot of money to AWS because I misconfigured some database stuff. You also end up with inconsistent states, right? If you get halfway through but your connection drops, or if you're dealing with two different teams doing things slightly different way, your state can get inconsistent. You have a desired state and an existing state, and it can be neither of those, or something else entirely. You get human error, right? People are notoriously unreliable, that's why we have jobs, or we're going to have jobs after graduation, and it requires a lot of effort. Again, we are caring about how we respond to our customers' requests. They don't care that we are setting up infrastructure. So what do? You move to infrastructure as code. You have your infrastructure declared declaratively in a file that declares your intended infrastructure setup. So some examples, Terraform, right? People like Terraform. I think they did some stuff which maybe went closed source, which nobody's that fond of anymore. But Terraform is probably the most popularly used infrastructure as code tool. You've got Ansible, another extremely popular one. People use that in their home networks all the time. And AWS CloudFormation CDK, because I had to sneak that in there. CloudFormation is effectively YAML style files of setting things up. CDK lets you use any programming language at all that generates CloudFormation from it. You keep it in your source control alongside your code, right? That way you have versioned statuses of your infrastructure. If you want to roll back to a previous state, all you do is undo the commit or roll back. If you want to move to a new state, you do a commit. It automatically gets set up. You know your infrastructure is in a good state. And it gets automatically executed as part of your pipelines. Known good state. CI/CD, who's heard of these terms? Can you define what CI and CD are?
Well, continuous integration and continuous development.
Fantastic. So, people think they're the same as automated deployment and distribution, right? If you go into any CI/CD tool, you end up saying, oh, CI means automatically updating your code. CD means automatically distributing your code in response to a button or whatever. That is not the case. It means you avoid long-lived branches and you continuously integrate and distribute, as the name is implied, small changes. If you make a change, if you make one tiny commit, it gets added to the main instantly and rolled out. So you do that through a series of environments, right? You have dedicated testing environments. As soon as your code gets committed, it gets sent to run those testing environments. You might have an alpha environment. This is the way we do it at Amazon, right? This is not a maximum for life. This is how I like to do it. It can be quite expensive because there's a number of environments. You have your alpha environment, which makes sure you don't break the beta. You call beta services and make sure you don't crash. You've got your beta environment, which is how you call other services and make sure it won't crash. Remember, we're in a service-oriented architecture here. You call other teams beta services. You've got your gamma, where you test with production data. Customer requests don't necessarily hit your gamma, but it deals with production data. It's entirely separate from your testing area, so you're not dealing with any customer information in testing areas, and it's another stage. And you've finally got your production stage. You will notice here that, no, that's another slide I'm thinking of, sorry. So you've got various deployment strategies when you're deploying to these different environments. Let's say we're still dealing with containers. You've got in-place deployment where you close down a container that has the previous version of the software and you spin up a new container with a new version of the software. That's tremendously efficient. You're not duplicating the containers. You're paying for the same amount of infrastructure the whole time through. You've got blue-green deployments, right, where you spin up extra containers. Your original one is your blue, your new one is your green. You have your load balancing between them, and you slowly swap over to the green service and then turn off the blue ones. That's tremendously useful for preventing issues in continuity, but it keeps things running smoothly, and it increases your infrastructure costs. You've got canaries, right, where first of all you deploy to one individual one. It's the canary in the coal mine, and if there's any problems with that, then you shut down, you revert back, all goes back to a known good state. So how do we know if things are in a known good state or a known bad state? I just talked all of that of, oh, you deploy slowly to make sure nothing goes wrong, but how do you actually know if things are going wrong? Well, first of all, failure happens, right? Happens to the best of us, and the worst of us, but mostly the best of us. Machines go down, right? That is a fact of life. Your code will break. You are not a genius. I'm not a genius. Nobody in this room is a genius, except maybe Hamish, apparently, from his answers to these questions.
It's about the first name.
Exactly. You will encounter bugs, right? Network connections drop. People with diggers will go through your fiber lines. That has happened to many data center companies. And global crises happen, right? I mean, if you go onto the AWS dashboard right now, this is what you will find. Because drones have hit the data centers in the UAE and Bahrain. It's a major issue. People have lost data because of this. And you need to be prepared for that. I don't think we need to be prepared for missiles hitting the London data centers, but still, all these other things happen. I mean, if we're in a global thermonuclear war, the first thing you want to care about is how your AWS service is still working. So how do we get information about our containers to know if they're up or down? Well, we use logs, right? Everyone loves logging. We don't log as much as we should. Log centrally in JSON. Get each of your services producing JSON logs. They're not necessarily human readable, but you feed them into a service, and that makes them human readable. You get more information with a little bit more processing. You have metrics, right? Your logs will contain metrics. You can count CPU, RAM, requests per second, HTTP codes, right? How many of your requests are successful 200 codes? How many 404s are you getting? Are people hitting an old endpoint that doesn't exist anymore? How many 500s, internal server codes? Watch these on a graph, watch spikes. At Amazon, every other Thursday, we look through our logs for the previous 2 weeks and our metrics. You'd notice these double daily spikes because people watch before work and they watch after work, watch a bigger one in the evening. Metrics are useful for so much. The Hollow Mountain, the power station in the Highlands of Scotland, has anyone been there? Well, it's awesome. It's a great big pumped hydro storage thing, and what they do is every time there's a football match on, at half-time, they have to open the gates, send water to the hydropower plant because everyone goes to put the kettle on, right? Know when your load is. Know when things are happening. Know what is happening with your service. If you're not being driven by data, you are gambling on smoke. Do traces. There's a fantastic tool called OpenTelemetry where if you're in that great big service-oriented architecture I showed earlier, you send your request in, it causes all these other requests to all different services. They're all tagged with the same ID. You can tell all of these hundreds of requests that spin out from that original request. You can see the life cycle of your user's request. Do health checks, right? Automatically restart services when they're not healthy. That's what load balancers do. Like we spoke about earlier, it's why DNS sucks the load balancer because it can't do health checks. There's an example of CloudWatch and other AWS services, other services are available about looking at spikes here. So you can tell, oh, I can probably scale down my infrastructure in the times between them because there's no traffic, but I really need to scale it in these times. This might correlate with something external. This might correlate with when people are coming home from work or whatever. And this is a Prometheus, a very, very popular tool for looking at logs and metrics. You can see various different charts here. This person's having a lot of traffic by the looks of it, not having a very good time. And then using that information, you can recover, right? The circuit breaker pattern is great. Anyone heard of a circuit breaker pattern? If your services are calling another service and persistently failing, then what you do is you hold off, right? Because one of the greatest things that happens is a thundering herd moment, where if a service goes down for a brief period of time, all those requests queue up, and as soon as it comes back on, you get hit with thousands of requests, that service goes down, you're even worse than when you started. In Amazon, there are specific services that act as circuit breakers to cache requests to other services. so that when you go down, you aren't hit by that great big thundering herd when you come back up. Use retries, right? Polynomial retry is great, where you first of all hit your server, and if it doesn't respond, you do some polynomial of that. You say like, not polynomial, exponent. You wait until that time squared or that time cubed, and that way it increases the amount of time you wait each time. You have a set threshold, say, oh, it's not responded in a minute, we can probably appreciate that this is down. Timeouts, right? Wait until your request has spent a certain amount of time being processed and go, oh, this doesn't work. Fail fast and fail loud, it lets you recover much quicker. Graceful degradation, right? Design your services to work if something fails. You'll notice if you go to any website and hit 404, it will not just give you the generic Google Chrome or Firefox 404 message. The website will have a nice 404 message saying, oh, would you like to go back to the home page? Degrade gracefully, let your customers know something's up, but that it's okay. And test your code, right? Test in production. Anyone been told not to test in production before? Well, everyone always tells you to not test in production. I can tell you with these types of tests, you absolutely should test in production. No matter how hard you try with your testing environments, you will never properly replicate your production environment. There are always tiny little things you'd never even think of. Do load testing, right? At Amazon, we had these things called game days, where every so often a team would hit an internal service with tremendous amounts of load, more it would ever handle in real life. And they would do that on our production systems to make sure it could handle that. Of course, robust controls in place in case it degrades, in case it stops working, but test your production systems. It's really useful. Do chaos engineering, right? Anyone heard of chaos engineering before? You run a small service that actively attacks your service. It takes down containers, it cuts network connections. Yes?
Is that what Netflix does for a lot of their stuff?
You're very smart, aren't you? We're getting onto that in a second.
Okay.
That's exactly what they do, yes. So you should be giving this talk. So yeah, you take down containers, you break connections, you sever things, you make everything that can go wrong, and see if it still works. Because remember what I said earlier, failure happens, design for it. Run experiments, try chaos engineering, see what fails. Have detailed hypotheses, have detailed end goals, right? Act as if you're a science student. This is Chaos Monkey here. This is Netflix's library for doing chaos engineering. It's a small monkey that lives in your system and takes things down occasionally. I call those my group project team members, but they have a specific thing for this. Nobody hears any group projects with me anymore, no. This is AWS fault injection service, right? It basically does the same as Chaos Monkey, but for AWS. If you're doing a great big test, you're supposed to let AWS know if you're using external tools, because it can look like an attack on their network. But this will directly break things for you in a controlled manner, and you can watch how it breaks and how it recovers. So, in conclusion, we're actually almost right on time. The big picture. Have your services like this, right? Have your load balancer at the start, have your containers or your lambdas, and then have a state store at the end. I've chosen DynamoDB because it's awesome, right? At Amazon, we're not even allowed to build anything with SQL databases anymore. It's a forbidden rule because they don't scale. But you are probably not Amazon, right? Remember at the start, when to use microservices, when to not, when to scale up, when to not. Use data, draw your conclusions from fact, not speculation. So each of these services is one of these. We call each other in this architecture. The client is calling services. We've got that diamond pattern again. We've got this calling this. Tremendous service-oriented architecture. Deploy like this, right? Have your code and your infrastructure being unit tested. Go into your alpha environment, getting integration tests, calling other services. Let's get into that. Until you eventually end up in production with your services that look like this, which are built up of things that look like this. So, in summary, the biggest challenges we face is our systems problems. I've not talked about writing a single line of code here, right? Only indirectly. All of this is systems engineering, systems thinking, especially in a world where LLMs are going to be writing more of the low-level code, regardless of what you think about that, it's happening. It's up to you to think about how to think systematically, how to think of the boundaries between things. Apply your individual programming techniques, like input-output, functional programming, to big systems. We are learning fundamental engineering techniques, not programming things. And you can do a lot by defining systems boundaries first, design by contract. Strive to automate things, right? Humans kind of suck at doing a lot of things. Get computers to do it. And the cloud is your friend. Use other people's products. Remember what your customers are paying you to do. Failure happens. Account for it. It's good to have something else there instead of failure, but I thought keep it PG. Any questions? Yes.
So, the whole crux of this talk, you presented like a path to success,
Yes.
so to speak. Yeah. So, it looks like this set of technologies, when done together, is the solution to things. This is rarely the case.
Yeah.
So when do these technologies are not the best fit? So, for example, microservices, containers, and things like that. So when are they not the best? What are their drawbacks?
Absolutely. So if we go back to the slides where I first introduced microservices, I'll not bother going back because there's 81 slides. We talked about how if you're dealing with these organizational pain points, if you're dealing with when your teams are stepping on each other's toes in the same code base, if you're dealing with not being able to separate things out in the commit history, that's when you move to microservices. If you're not dealing with these sorts of problems with a big team dealing with big amounts of requests, that's when you start thinking, okay, maybe I can not bother with all of the scaling. The key thing is the metrics, right? Observe your data. If your customers are getting hit with errors, if your customers are not having a good experience, that's when you start to do things. All of this is focused around what does your customer pay you to do? What does your customer want you to do? Whatever allows you to most gracefully handle their requests. So if you are writing, it's not even just that, if you're writing embedded software, you never need to touch the cloud, right? When I was at VTech, we didn't even think about AWS. If you're writing a desktop application, you probably don't need to think about the cloud or microservices. At the start, the modular monolith, I still maintain that almost regardless of what you're doing, that is better than an unstructured monolith. One of the few cases where it's almost like a defined solution, in the same way that not hitting your leg with a hammer and hitting a nail instead is a defined solution. But really, it's about when you're having difficulty scaling technically and operationally, and when your customers are being impacted.
Regarding the monolith side, I mean, if you have people building different libraries and you just dynamically hook them all together, that's not a monolith, as I understand it. So, what is the benefit of microservices in that case? Because basically, it's just separate libraries.
Yeah, so that's actually where the definitions start to get blurred. I think I know what answer you're trying to get me to give, which is that when...
Oh, no, I'm not doing that.
So, well, the textbook answer to this is the fact that when you have different aspects of your system that need to scale at different levels, or need to operate with true operational independence. So let's say I'm Amazon and I run different products, not products, different services to my customers, right? I have Prime Video, I have Amazon Shop Front, I have Amazon Prime, and these different things have some components in common that need to scale much higher, but they also have their individual components that don't need to scale so high. That's a great example, because you can independently scale different sections. However, modular monoliths and microservices, the line gets very blurry. So I don't know if I did mention, the idempotency to other services. There's a great talk by one of the engineers at Starling Bank talking about their ditto architecture, do idempotent things to others. What he also talks about is the fact that although they effectively treat their things as microservices, they actually, until very recently, deployed as a monolith. So although they were organizationally microservices and they were each making different libraries that communicate with each other, they deployed as a single package. So the lines get very blurry, and it's really about individual operational needs.
Yeah, that last bit sounds very sensible, actually.
Yeah.
And I was thinking, does anybody do that?
Yeah, tons of people do it. It's a really great way to write software. Lots of the biggest problems in software are not actually technical. I understand you do lots of translating equations to code and so on, some of the awesome technical stuff. However, I'm personally more interested in the areas like this, where the issues are, how do we deal with a large system with lots of different people working on it? At, say, Amazon or Google or Facebook or anything, the engineers you'll find, the reason Bang has such a reputation is not because you end up with people who are the best technically. It's because you end up with people who know how to deal with these sorts of problems where you've got different things talking to each other, different groups talking to each other, where you have this team owning this service and this team owning this service and how you coordinate them. And so most of this is an organizational issue.
Yeah, that makes sense.
Yeah.
All right. Thank you very much.
Any further questions?